So today we have a seminar by Sean Hartnoll from the University of Stanford, who is on sabbatical in Germany, in Dresden. We were hoping that he could come in person to give the seminar, but due to the never-ending pandemic, he's in Dresden, but has been kind enough to accept to give the seminar by Zoom. So the title of the seminar is A Classical Interior of Black Holes in Holography, and this is connected with the lectures in that inside black holes there are singularities. We are not sure that we know exactly what these singularities are, but if they are space-like, there are good reasons to believe that the BKL analysis could probably be useful. But there are more interesting features than just singularities. We have also sometimes inner horizons, and I think that all this structure will be discussed from the holographic point of view in the talk by Sean. So please go on.
Thanks a lot, Mark, and I certainly hope to make it in person sometime. That would be great. Just before I start, the other thing is I don't know how you want to do the questions, but I'm certainly very willing to take questions as I go. I think that is often the most natural. So is there a way for us to do that, Mark?
Yeah, I think that probably I would have to repeat the question in the microphone, but there is definitely a way to do that. I think you can hear me, right?
Yes, yeah, I can. Okay. Yes. So please feel free to ask questions.
So if you have questions, interrupt, ask me, and I will repeat the question in the microphone.
Okay. That's right. I'm very happy to be interrupted. That's fine. Very good. So I will tell you a bit about the classical interior of black holes in holography. The material I'm going to cover is in these three papers that started off. This thread started with this paper, which is with a graduate student at Stanford, Alex. Jorrit is a postdoc at Stanford, and Darius, who was then an undergrad at Stanford, is now starting his PhD at MIT. And then luckily later we were able, Jorrit and I teamed up with Gary Horowitz and George Santos to do the remaining two papers. So because I'm not entirely sure where the audience is at, I'm going to give a very brief background to ADS CFT and holography so that everything has been introduced. So just before I start this, there's a few comments about what ADS CFT is. So we're concerned with spacetimes that are asymptotically anti-de Sitter. That means along distances they approach the anti-de Sitter spacetime, which in the Poincare coordinates that I'll be using means it goes like this. So here the boundary infinity is as z goes to 0, and so z is like the radial coordinates. This is time. And then this is ADS 4. Okay, so my talk's going to be in 4 space-time dimensions. And so you have two transverse directions, x and y, and you have time. And then z is this radial direction. And as you go towards the boundary, ADS grows very quickly, right? That's this 1 over z here. So asymptotically, ADS is some space-time that approaches this behavior near the boundary. Now, the ADS is the main reason that ADS is useful is that it acts like a box. Okay, it's a box that relativists like. Because if I really have just a box, then I need some coordinates to tell me where the box is. But ADS plays the role of a box because this boundary at infinity is so big that it can be treated as rigid. And so it has a time-like boundary that is fixed. And so you can imagine an observer sitting at infinity in ADS at the boundary. Okay, so there's some observer at the boundary away at infinity, and that observer can grab the boundary and shake it, okay, and that will send some source. For example, some gravitational waves could be emitted into ADS from the boundary. And then what will happen? Well, some of these waves will go through, and maybe they'll fall through some horizon that might be deep inside the spacetime, and some of them will get reflected back to the boundary. And then the waves that are reflected back to the boundary, the observer at infinity can see them, and that's the response, right? So an observer sitting at the boundary of ADS can perform an experiment, which is like sort of look at a correlation function, right? You emit a source, and you get a response. Okay, so that's the basic thing that ADS lets you do. It gives you somewhere well defined that the observer can be to do this kind of experiment. And of course, as you go in, there's an increase. So the redshift would be infinite coming from the horizon and 0 at the boundary. And so what ADS does is it geometrizes the energy scale. Processes that happen here are very redshifted compared to the boundary. And so for the boundary observer, things that happen here are low energy processes, whilst things that occur near the boundary are high energy processes because they're less redshifted relative to an observer at infinite. Okay, so that was one page about what ADS, anti-de Sitter space, is the space-time, and what's most important about it is it has a nice boundary. Now, what the ADS-CFT duality or the holographic correspondence states is that this response that is measured by the observer at infinity is equal to the response that you would measure in a certain strongly coupled quantum field theory with no gravity in it. Okay. And so you can, if you like, I'm going to go back. Oops, sorry. You could take all this gravitational stuff and this source and response, and you can replace all of this with some non-gravitating field theory. Okay, and ADS-CFT duality states that there's an equivalence between the gravitational dynamics probed from infinity and a non-gravitational system. And the way it works is that sourcing some given field at the boundary of the space-time, well, this field could be a graviton, right? It could be gravity, it could be electromagnetism, it could be some scalar field. Sourcing that field at the boundary corresponds to taking your quantum field theory and deforming it by some operator. So the act of shaking the boundary, of putting in a source to the boundary, is equivalent to taking your quantum field theory and deforming it by some dual operator. So for example, if this field were the metric, so a deformation of the metric at the boundary of the space corresponds to deforming the field theory by the energy momentum tensor, okay, which would be the operator dual to the metric. So the point of all this is that gravitational dynamics in asymptotically ADS spacetimes can be reinterpreted as a non-gravitational system. And because non-gravitational systems are better understood than gravitational ones, this kind of correspondence is useful for thinking about quantum gravity. Okay, so that's my one very, very brief introduction to ADS-CFT. I hope it was useful. So now within this context, let me say a few words about what black holes mean. And I want to just talk about what the exterior of the black hole and what the interior of the black hole means. So here is a Penrose diagram for, let's say, Schwarzschild black hole in ADS. And so here you have, this is your space-like boundary. Okay, here's the horizon, here's the past horizon, this is an eternal black hole. Here's the inside of the black hole, here's the singularity. As many of you hopefully know, in black holes, you naturally get this doubling of the boundary. There are actually two boundaries. And this is related to the fact that black holes describe what's called the thermofield double state. And actually this goes back to the 70s. And yeah, actually, I think it's useful to think about it in the old language. So if you consider a slice that goes across like this, and you consider a quantum field that lives on that slice, there's some boundary conditions. Actually, maybe you could even take this slice if you want. It doesn't have to go right through there. There's some boundary conditions at the horizon that the field has to obey. And what those boundary conditions end up doing is entangling the field on the two sides of the horizon. This was the content of this paper by Israel. And so what you should think of a black hole as is two copies of the field theory. One lives here, there are two boundaries. That's here and here. And they're entangled in a certain way, which is this Boltzmann factor. And so this thing is called the thermofield double state. Okay, and so that's what a black hole is in ADS-CFT. That's not going to be too important for what we're doing, but it's true. Now, so what is the meaning? So by the exterior, let's just focus on this exterior here. So suppose I have an observer that's sitting on this boundary, and is doing this experiment of throwing in something and seeing what comes back. What do they measure? Well, the basic thing they're going to measure is this quasi-normal ring down. So if there's a black hole sitting there and I throw in a stone, and then I see what comes back to me, the gravitational waves that will come back to me are going to have some damped oscillations. That's called the quasi-normal mode. I'll see that the black hole wobbles a little bit and then finally settles back down to equilibrium. And in fact, this is the LIGO signal. Okay, this is exactly what was seen. And the last steps, the LIGO signal is this quasi-normal ring down where the black hole oscillates and then it reaches equilibrium again. And so in ADS-CFT, what that means is the exterior dynamics, the gravitational waves that are emitted by the black hole as it reaches equilibrium. What it describes in the field theory is the approach to thermal equilibrium. Okay, this quasi-normal ring down is the approach to thermal equilibrium. And this has been understanding this has been a rich source of inspiration for how to think about strongly coupled quantum field theories. And so that's not what I'm talking about today, but we wrote a whole book about it that I encourage you to read. So what I'm trying to say is that the outside of the black hole, it's understood what that means in holography. What it describes is how a strongly coupled field theory reaches thermal equilibrium. Okay, that's the outside. But today, I want to talk about the inside, which is here. Okay, so one more time, the outside of the black hole is just completely understood what it means and what it does. Okay, but the inside is tied up with very deep questions, such as in ADS-CFT, how do you describe an infalling observer? Because remember, here was the Penrose diagram. Someone that falls into the black hole is no longer in causal contact with the boundary. And so it's a bit hard, it's conceptually confusing how you describe that from the boundary point of view. It's also tied up with, as Marc Henneaux mentioned, with what does the singularity mean? And it's also tied up with confusions in quantum cosmology if you think of the interior of the black hole as a kind of time-dependent cosmology, a la BKL, which we'll come back to. Now, despite those difficulties, there's been a lot of excitement, in the last decade or so about how to try to see behind the horizon from the boundary. And one perspective is that you really want to use both boundaries. And I'm not going to go into this because it's not too crucial. This is more of a motivation. And so there are certain observables which use both boundaries. It's a certain entanglement, but it's not important. What it amounts to is you end up considering a minimal surface, a soap bubble that stretches between these two boundaries. And that bubble can go through the interior of the black hole. And the answer you get is the area of this soap bubble. It is supposed to be a minimal surface. And it turns out that these are related to certain entanglement quantum information theoretic quantities. Okay, so it seems like it is possible to probe behind the horizon in ADS-CFT, but you need to use both boundaries and you need to ask certain quantum information theory type questions. Okay, so yeah, let me just leave it at that. I don't want to go into it. It's mainly a motivation that it looks like it might be possible to see behind the black hole. So this motivates, if you can see behind the black hole horizon, what will you actually see? So it's been known for a long time, as I think you've been seeing in other lectures in this course, that the interior dynamics of black hole as you approach the singularity is extremely rich. And the BKL is a famous example of this. But almost all the studies that people have done in holography of looking behind the horizon have just used the ADS-Schwarzschild solution. But the interior of ADS-Schwarzschild is actually unstable. So let me go back to, maybe I'll draw it here. So one more time, here's this diagram. If I make a small perturbation here, the exterior just goes back to being Schwarzschild again, right? The energy falls into the horizon, the black hole grows a little bit, but then it goes back to being Schwarzschild again. So if somebody sneezes outside the black hole, nothing bad is going to happen. If someone sneezes inside the horizon, however, that will make a big difference to future infinity because the perturbations actually grow in the inside, as I'm about to show you. And so the inside of a black hole is not stable. And in the Schwarzschild context, there are mathematical papers on this, but it should be obvious from this BKL behavior that I think you've talked about that black hole interiors tend to be chaotic and unstable. And so all the papers that have been written in a holographic context on the interior use Schwarzschild ADS, which is an unstable, and even though it's stable outside the horizon, it's unstable behind the horizon. And so it's not the right interior to be looking at, right? The Schwarzschild ADS solution should be irrelevant at late interior times because it's unstable. Yeah, so one more time. If someone is sitting behind the horizon and sneezes, that will completely change the future infinity, okay? In a way that we'll see. Now, while the interior dynamics has been widely studied by mathematicians, it has not, in a holographic context, it hasn't been studied. And in my mind, and this is just a classical question, right? It's about how do Einstein's equations behave as you approach a singularity in the inside. And I would like to argue that understanding a generic classical interior is logically something that you should do before trying to study quantum gravity questions related to the singularity. Okay, so singularity resolution is obviously a big topic in quantum gravity, but if we don't understand classically what the singularity looks like, then we're not going to get the right answer. Okay, so this talk is going to be about what happens to these singularities classically inside these ADS black holes. So the plan.
There is a question.
Yeah, please.
Okay, and I repeat the question. So the question is how much ADS is important for analyzing this question, since the interior of the black hole would be the same if it's asymptotically flat.
Thank you. No, you're absolutely. Thank you. I was going to come to this, but you're absolutely correct. And so indeed, we'll see in a minute. I hope the next 5 minutes will answer that question actually. But it is correct that the near singularity behavior, the cosmological constant actually drops out of the equations, and so the behavior that you get here does not depend on it. Is not going to depend on it being an ADS. However, what I'm interested in is how this behavior gets embedded into ADS CFT, and we'll see that it motivates a certain way of looking at it. But it's absolutely correct, and thank you for mentioning that the behavior near the singularity actually doesn't care about whether it's an ADS or not. Yeah, thank you. Good. So today, what I want to do is I'm going to take a few steps towards a more generic classical interior, again, as opposed to Schwarzschild, where the interior, again, I mean, maybe for this audience, it was already clear given the previous lectures, but I think it's not clear in general. Schwarzschild is a great model for a black hole outside, but inside it's a very special unstable solution that we shouldn't be too focused on. So I want to take a step towards a more generic interior that are tractable, meaning that I don't have to do very complicated stuff with PDEs, and that are holographically motivated. That relates to this question. We'll come back to that in a minute. And so everything I'm going to do today is still going to be spatially homogeneous. Okay, that's the tractable part. Okay, I'm going to keep symmetries in X, Y, and T. Are going to still be translation invariant, whilst a truly generic interior is expected to be very inhomogeneous. Okay, nonetheless, even within this homogeneous context, we'll still find some very rich beyond Schwarzschild behavior, if you like. All right, and so there are 3 steps corresponding to those 3 papers that I mentioned. First, I'm going to talk about neutral black holes. Then I'm going to talk about charged black holes. And then I'm going to talk about charged black holes with charged matter fields. Okay. So let me start with neutral black holes. So the starting point was the following. I told you that something you can do in holography is deform the boundary, right? You can turn on a source at the boundary. And if you turn on a source, remember in a quantum field theory, that means you have your quantum field theory. It starts off as a conformal field theory, not too important for my purposes, and then you deform it. Okay, And so you add some operator to your theory, and this is the source. Remember, the source is the boundary value of the field. Okay, and I'm going to take a perturbation. It doesn't depend on time or space, right? It's a deformation. So it's not a deformation in time. It's a deformation of the theory. Okay. Now, what does the deformation of a theory do? It induces a renormalization group flow, right? So if you start at a fixed point, that scale invariant, and then you deform it, this coupling starts to run. In holography, the running of the coupling is the radial evolution of the field, right? So here's the boundary, here's the interior, this is the z coordinates. And so I deform the theory by having some boundary value for this field, but then I have to solve Einstein's equations by integrating in this field given the boundary value. And that will give me some phi of z. And that has the dual interpretation of the renormalization group flow of this coupling. Because remember, here is low energies and here is high energies. Okay, so the setup I want to do is take the boundary of ADS, deform it by turning on a field, and then solving Einstein's equations to find how this field evolves as you go in. All right. Now, what people normally do, this is called holographic renormalization group. Okay. Now, what people would normally do is take the boundary and then integrate, and then they would stop at the horizon, because the horizon is it's infinite redshift to the boundary, right? It's far away. However, from a relativistic point of view, a GR point of view, there's no reason things don't stop at the horizon. And so I'm just going to keep going and integrate through the horizon. And then I want to ask, what does this do to the singularity? Actually, let me change the order a little bit. So let's just look at this picture. Ignore the text. Just look at this picture for the moment, right? So this is what I meant by holographically motivated. I'm going to do something that's very simple in holography, which is to take the boundary and deform it. And then this deformation will change the space-time. I'm going to integrate in, I'm integrate through the horizon, and then I'm going to ask, how does the singularity change when I deform the boundary? Okay. So maybe this will be more, I'll show you how it actually works, and I think that might be more concrete. So this is the simplest thing you could do in a holographic context. So what do you do? So in gravity, right, in 4 dimensions, what I had to begin with was, this is gravity with a negative cosmological constant that has ADS as a solution, right? And now I'm going to take the theory to also include a scalar field with a mass, a free scalar field with a mass. And I'm going to take the scalar field and I'm going to insist that it's not 0 at infinity, all right? And then I have to integrate Einstein's equations in to see what happens. And so I'm going to look for a black hole solution, which will look something like this. So now remember in ADS, another nice thing about ADS is that you can have these planar black holes, okay? So X, which is just makes things a bit simpler. And so there's X and Y are the boundary directions. This is time, and Z is the radial direction, right? So here's the boundary, okay? And this is in units of Z over ZH, so this is a horizon. So here's the scalar field. Okay, I know it looks like it's going to 0, but its derivative is not going to 0. So it turns out that's the right notion of sourcing it. So the scalar field runs, and then we get to the horizon, and we just keep going. Okay, so I hope this is clear, right? I'm solving the Einstein scalar coupled equations, insisting the scalar is non-zero at the boundary, and then integrating in. And I don't stop at the horizon, I just keep going. And so this is what the phi looks like. And these are various metric components that also change. So the dotted line is the Schwarzschild solution, right? So the Schwarzschild solution has no scalar field. And also this chi is also 0 in Schwarzschild, right? Schwarzschild has the form f dt squared dz squared over f, right? These things are the same, but more generally, it doesn't have to be the same. And so when the dotted line is Schwarzschild, and these solid lines are what you get with, this is just numerical, but it's ODEs, it's not PDEs, right? ODEs means it's something that I can do on a laptop with no difficulty, right? It's almost analytic as far as I'm concerned. It's very easy numerics, okay? So what do we see? So the reason I'm plotting this particular quantity, which is the sort of logarithmic derivative, is that the fact that these things are being constant at late times. Oh, I should have said, when you go through the horizon, z becomes a time-like direction, right? As you go through the horizon, z and t swap over. And so the evolution here is in space, but the evolution here is in time, okay? And of course, to show that this black hole is regular, you should go to some classical-like coordinates, okay? But everything's fine. I'm using these coordinates, but you can check that if you go to some infalling coordinates, everything will be regular. Right. So here, this is time evolution, okay? Because z is now time, and there seems to be some kind of scaling behavior at late times. So that we can understand analytically. And in fact, so here we started off here at the boundary. I turned on a source, I integrated in, and it turns out that things scale near the singularity. And in fact, the scaling is precisely the Käsner solution. Okay, now, did I not write this? Okay, sorry, 1 second. Käsner's coming. Okay, which I'll tell you more about in a minute. So there's some scaling near the singularity. And so I want to think about this. It's kind of interesting from a renormalization group point of view, that normally we think that the boundary is the UV, the high energy, the horizon is the low energy, but going all the way to the singularity is like some trans IR, okay? It's like it's a different place, but there seems to be some scaling here. And for example, the metric coefficient has a scaling exponent, which I'll come to in a minute. So let me tell you what happens near the singularity. So what we recover near the singularity is this Käsner solution. And so Käsner, I realized when I write this that this is the first time ever in a talk that I should specify the century. So the Käsner solution is from 1921, not 2021. Okay, it's one of the oldest solutions in exact solutions in GR. Okay, and it describes, if you write it in terms of tau, which is the proper time for the singularity, it looks like this. And I'm going to retain isotropy in these two directions. So there's time, and there's now t is now a space coordinate that has some exponent, and there's some other exponent here. And these exponents have to sum up to 1, and their squares have to sum up to 1 as well. There's some constraints. And the scalar field goes logarithmically. And so this paper added the scalar field to the Käsner solution. Okay. So what is being, so I would say there's a flow, a renormalization flow from ADS at the boundary to Käsner at the singularity, okay? And these exponents, PT, Px, and Pφ are related by some algebraic relations. And so there's only one free exponent, which we can think of as PT. And so this exponent PT has to go between -3 and 1. -3 is the Schwarzschild singularity, and 1 is like a Rindler. It's not a singularity. It's null. It becomes null. And so here we can make this plot. So this is the deformation of the boundary, how much you turn on the scalar field at the boundary, and this is the singularity, the exponent, the Käsner exponent at the singularity. And just to show that Schwarzschild is here. When you have no scalar field, you get the Schwarzschild value, and then it has some profile. Okay, so what this is, well, I found this useful. I think maybe none of this is extremely surprising in retrospect, but this is a extremely tangible way of seeing that the Schwarzschild interior is not generic. So you simply, as you deform the outside, the singularity also gets deformed. Okay, and the way to think about it is there's a Käsner exponent at the singularity that depends on the deformation of the boundary. And we have this, what's also a bit nice, I think, about these planar black holes is that, okay, I mean, it's numerics, but there are three numerical functions. And so it's a very explicit evolution from ADS to Käsner, all right? Okay, so that's the first story. So it's perhaps not surprising that we find some Käsner scaling near a homogeneous singularity. It's a very explicit realization of Käsner in a holographic context. You get it. So if you deform the boundary field theory, you get a generic Käsner thing in the interior. it shows that the Schwarzschild interior is not generic. I don't know the answer to this question, but it's suggestive to ask whether this scaling has anything to do, what the meaning of this scale invariance at the singularity is for the field theory. Now, I think you probably have heard about bounces and chaos and so on. So within this setup, there are no bounces. It's just a simple evolution. And I think that's because this ansatz, it's a torus, right? I think to start having interesting things happen, you need to have a more complicated homogeneous space. And here we just have t, x, and y. And these just go to Kastner. There are no walls and there's no chaos in this setting, okay? We'll come to some chaos later, but in this theory and with this symmetry, with this symmetry, it just devolves to Kastner, okay? And that's an exact, Kastner is an exact solution. Are there any questions about this part?
Maybe I have a question.
Yeah, please.
So there is a relationship between PT, the Kastner exponent PT, and the boundary value of the scalar field that you can, I guess, that you can work out. I mean, is there a one-to-one correspondence between, if I give you phi at the boundary, can you tell me what is PT or?
Let's see. Yes, it is in that. It's not one-to-one. So it's this plot. And so, I mean, it is, you know, this did come from, yeah, it did come from solving, yeah.
But is there, okay, then my question really is there a value of phi 0 so that PT is positive? Because you said
we'll come to that. Yes, not in this theory. So that, yeah, thank you. I had the comment, but I didn't. So within this setting, you can prove and verify, but you can actually prove this, that PT has to be negative, okay, is negative. And so what that means is that, let me take the Penrose diagram again. So let me call this region the Einstein-Rosen bridge. Okay, the word is used differently by different people, but so I can do this across. Let me take like a Cauchy slice like this, and then you can take a sort of a family of slices, and GTT, right, is this direction, right? So the size of GTT is a measure of how much distance there is sort of going across the interior, right? Because the T direction is this one in the inside. This one is T. So the fact that PT is negative means that as tau goes to 0, it means that GTT is growing. I mean, that's not obvious from the Penrose diagram, right? Because that it's about the causal structure. But the interior is growing at late times. And that's what PT being negative means. But we're going to come to cases later where it also can be positive. So I thank you. That's also a good question. So once again, in this framework, PT is always negative, which means that the interior of the black hole is growing at late times. But we'll come back. We'll see that doesn't always happen. Is that your question?
Yeah, thank you.
Yeah. Anyone else? If I've like lost anybody already, I'll also be happy to take simple questions if there's a simple question.
There is a question. Maybe you can read it. Oh, it disappeared. Can?
Oh. Is it there?
Discussion. So maybe you can see it in the discussion.
Yeah. Let me. Where's the discussion? Chat. Yeah. Very good. Does this scaling depend on when the perturbation? Right. So I did say, but let me say it again. This is not a perturbation in time. So this perturbation on the boundary is like a coupling in a field theory. It's constant in time and constant in space. So it's always there. It's not being turned on at some time. Okay, it's like you're changing the theory on at all times. Yeah. So yeah. Very good. Perfect. Okay. So wonderful. So that was, I think, pretty simple. Right. So the main point, I think, is that it illustrates that if you do something generic outside the black hole, you get a more generic singularity inside. Okay, that's the main point. Okay, but now let me talk. Things start to get more interesting for charged black holes. So charged black holes are, so I told you that a normal black hole is this thermofield double state. That just means it's the canonical ensemble, right? It gives you the canonical ensemble of the field theory. If you add a charge, that means you're adding a chemical potential, which means you're in the grand canonical ensemble. Right. Now, what's well known for the inside of charged black holes like Rice-Nordstrom is that you get these Cauchy horizons. So let me talk you through that first. So here's the boundary. Let me make a different color maybe. So here's the boundary. Right, those are your two boundaries. Then, as you go in, you have a horizon, the horizons, just like before. Okay, and you can go through it. But if you go through the horizons, you don't find a space-like singularity. Instead, you find another horizon inside the black hole. And if you go through that, then you find a time-like singularity. Okay, this is in the Rice-Nordstrom solution. And then of course you can keep going, and it looks very exotic because there are all these infinitely many universes that you can go into. So it's been conjectured. So mathematicians have never liked this because it means the Cauchy problem is not well defined. Because if you go through this horizon, you suddenly can get hit by things that come out of the singularity, and those are not. So if you set your initial data on some time slice and also the boundary conditions, you can evolve. But when you go through this inner horizon, you can suddenly get hit by stuff from the singularity, and you don't know what that is, right? And so your solution is not specified by the initial data, and the Cauchy problem breaks down, and that's why these are called Cauchy horizons. And so it was conjectured by Penrose that these Cauchy horizons are an artifact of the fact that you found a highly symmetric solution, and that generically they shouldn't exist, okay? Or they should be, another way to say that, they should be unstable. And that's pretty reasonable. And in fact, I think, this is an extremely misleading picture of what the charged black hole looks like inside. And it should just be banned, okay? Or something. It's not a helpful picture. It is helpful in that it triggers thoughts, but it's not the answer, as we'll see. So we're going to ask the following question: do charged black holes of the deformed theory? So now suppose remember here was the boundary. Here's the boundary of ADS. Suppose I deform this boundary to make it more generic in the same way I did, and I again integrate in through the horizon. Then I could ask, does this Cauchy horizon survive, or does the back reaction of the matter fields destroy the horizon and maybe make some kind of singularity across here? Okay, that would be what cosmic censorship would suggest. And so this is a holographic version of cosmic censorship. So cosmic censorship is this conjecture. Okay, there's a strong and a weak cosmic censorship, but strong cosmic censorship is the conjecture that Cauchy horizons are non-generic. And so the way the mathematicians normally think about it is that you pick some initial data, and if you take generic initial data, Cauchy horizons do not form. Okay, I'm doing a slightly different version where I'm saying, what if you there's no time evolution in what I'm doing. Okay, there's no time evolution in the outside at least. So I'm saying, what if I take the boundary conditions of ADS to be more generic and I integrate in? Do I find a Cauchy horizon inside the black hole? It's quite closely related, because when you get to the horizon, the boundary conditions become initial conditions for the inside. Okay, so they're quite related, but it's a little bit different from how it's normally formulated. It's like a boundary value version of cosmic censorship. Okay, so I'm going to do the same deformation that I did before, but now on a charged black hole. Okay, and let's see what happens. So the theory I'm solving is almost like before, right? I have gravity with a negative cosmological constant. I have the scalar field that's going to run, that's my deformation. But now I'm also going to add a Maxwell term, okay? Because I want to consider charged black holes. Now, at this point, I should tell you something, that in ADS, the mass squared is allowed to be a little bit negative, okay? You don't automatically get an instability, and it's because ADS is like a box, and boxes cut off long wavelength instabilities. And so it turns out in ADS, the mass squared is allowed to be a little bit negative. It's something called the Brighton-Lohner-Friedman bound. But so if it turns out if the mass squared is negative, these correspond to perturbations that grow as you go into the bulk, into the interior, whilst if the mass squared is negative, they get smaller as you go in. For that reason, ones with mass squared being negative are called relevant deformations. So for that case, we can actually prove in one line that there's no Cauchy horizons, okay? And it goes like this. So remember, F is like GTT, right? It vanishes on horizons. So suppose you did have two horizons, an inner horizon and an inner horizon. And remember, Z is getting bigger as you go in. This quantity, it turns out, would vanish on a horizon because it has a GTT in it, essentially. So its derivative integrated between two horizons gives you the value on the two horizons, which is 0, if there was a horizon. So you get 0. You can use the equations of motion to expand out this derivative, and you write it like this. This is just equations of motion give you that. The wave equation for phi gives you that. And now F is actually negative because we're between the horizons. So GTT has the opposite sign. And so if this mass squared is also negative, both of these quantities are negative definite and they can't be 0 unless phi is 0. And so actually, to some of you, this may not be useful. This is extremely similar to how you prove no hair theorems for black holes on the outside, but it's on the inside, okay? And so we can, for example, this proves, I mean, this is probably a little bit fast, but maybe you can at least get a flavor of it. It shows that when m squared is negative, there cannot be a Cauchy horizon inside the black hole. When m squared is positive, it turns out there can be Cauchy horizons, but they're not generic. Meaning, in terms of the deformation parameter, there are certain discrete values where you can get Cauchy horizons, but it's not generic. Let me tell you, well, unless people are very interested in this point, I think I'll move on. Okay, I think maybe I can come back to it. I don't want to. It's a bit tangential. The more interesting thing is what happens when there's not a Cauchy horizon. Okay, and so then you can just go back and do the numerics again. And if you do it, you find that the space-time looks like this. So there's again the boundary. There's the horizon. And as you go in, you go through this region that I'll come to in a minute that we call the Einstein-Rosen bridge collapse. I'll come back to that. And then if you keep going, you eventually get to a Käsner singularity again. So the generic interior of a charged black hole with this source on the boundary does not have a Cauchy horizon inside. It instead has a Käsner singularity, a lot like the neutral black holes. And in case this is also confusing to you that it bends up, you should know that actually, even Schwarzschild, although Penrose diagrams are often drawn like this, that's actually wrong. And actually, if you actually do the conformal projection properly, the singularity can either bend up or down. Okay, it doesn't have to be a box. Okay, let me come back to this region in a minute. Okay, but basically the causal structure of the charged black holes, once you get rid of this, the Cauchy horizon looks basically the same as the neutral black holes, except that this Käsner exponent actually now is always positive. And so here's a plot that's analogous to the previous plot. So this is PT. This is the deformation of the boundary. This is the temperature, and mu is the chemical potential, which is the value of A of T at the boundary. It's like the charge. It's in one-to-one corresponds with the charge of the black hole. I think mu is more natural because that's what you fix at the boundary, but it is the same thing. So it's a two-dimensional plot now, okay? So remember that the plot we had before that had PT against phi that looked like that, right? Now it's a two-dimensional plot because it's charged, and so you have two dimensionless ratios. The deformation in units of the chemical potential and the temperature in units of the chemical potential. Don't worry about the dashed line. And so what we see, right, so PT is now always positive, which means that this Einstein-Rosen bridge, this region, gets smaller as you go towards a singularity. Hopefully that should make sense, because when you had a Cauchy horizon, which is null, then the length of that is 0, right? A null surface has 0 length. So if you imagine just resolving so as you go towards a Cauchy horizon, these lines actually become shorter, right? The proper distance becomes shorter. And so the Cauchy horizon is not there anymore, but the Kästner singularity sort of remembers that, if you like, and the space-time, these lines get smaller as you go towards the singularity. So the Einstein-Rosen bridge shrinks as you approach the singularity. And let's just remember that it goes towards 1. PT equals 1 corresponds to like a Rindler, like a regular space. It's not actually a singularity at all. So a horizon, written in terms of Kästner coordinates, a regular horizon would have PT equals 1. I could talk about this a little bit, but actually what I would like to tell you a little bit about is this region. Okay, so the first point, very good. So first point is there are no Cauchy horizons. Second point is that the Einstein-Rosen bridge now shrinks towards the singularity, but it's still Kästner. It's still Kästner. And the third point is that there's this fun Einstein-Rosen bridge collapse I want to tell you a little bit about. An interesting limit is when the scalar field at the boundary is very small. Because that means the solution is almost Schwarzschild, it's almost Rice-Nordström everywhere. And you start getting very close to the Cauchy horizon, right? And it's still Rice-Nordström, but then suddenly it learns that there's not allowed to be a Cauchy horizon. And there's a very strong back reaction of the scalar field, a very abrupt back reaction. Does that make sense? So this is a very nonlinear effect, right? Because the smaller the scalar field, the closer you get to forming a Cauchy horizon, and so the more extreme the back reaction is. And so it turns out if you take the limit where the scalar field is small, we actually could solve this back reaction analytically, okay? Because it turns out it happens very abruptly. And that's why we call it the collapse of the Einstein-Rosen bridge, right? So so we have this diagram one more time. And so here would be the Cauchy horizon. And so the scalar field is integrating in, but there's some point where there's suddenly a very strong collapse. So let me show you how that goes. So we were able to do that analytically, and I insist it's very nonlinear because the smaller the field, the faster it happens, okay, which is and that cannot happen in a linear equation, right? We actually got an analytic solution for GTT, is given by this, as you go through this collapse. And so beforehand, as you approach the collapse, GTT is vanishing linearly, right? Because that's like a horizon, right? At a horizon, GTT would vanish linearly for the inner horizon. But then suddenly, at a very short time, proper time, it becomes exponentially small. Okay, so it doesn't go to 0, but it suddenly swoops down. And how fast that happens, it gets faster the weaker the value of the scalar field at the boundary. And so here's some, just to show that it's true. So again, this is GTT against Z. And the blue line is a numerical solution. Look, note that this is a logarithmic axis, right? And the red line is this analytic solution, right, which just captures this kink. So there's like a kink in how GTT behaves in the interior. So there's some interesting nonlinear dynamics that we were able to do analytically. This will be important later, actually. Okay. All right. So that was good. I think we're doing. Good. We're doing good for time. So now this is a summary of the charge case. So deformations of the boundary generically remove Cauchy horizons, and so you get Kästner asymptotics and a simple Penrose diagram, not this infinitely repeating thing. And again, it's just very explicit, right? It's just some ODEs and you're done, right? So again, it's not surprising, but it is nicely explicit. And I would call it a holographic perspective on some of these cosmic censorship questions. And then, as I told you a little bit quickly, perhaps, we found the analytic description of a certain nonlinear process, which is this collapse of the Einstein-Rosen bridge. Okay, so this is also another natural point for if there are any questions.
Maybe I have one. So the coupling, I mean, the action that you took for the electromagnetic field was just the standard Maxwell F² term. Could you put some exponential of the scalar field?
Yeah, wonderful. Thank you. Yes, yes, indeed. So the question is putting in like some e to the phi, some dilatonic coupling.
Yes.
And actually, we have a section, we did do that, and we have a section in the paper on it. And actually, I should maybe say, actually, it was known back by I guess Strominger and Horowitz that in flat space, this coupling actually already removes the Cauchy horizons, and you get a variable Kasner exponent at the horizon, at the singularity. And when you add that to this deformation at the boundary, yeah, there's some nice story that okay. I mean, it's qualitatively the same, but we have a section in the paper on it.
Okay, and but would you?
Yeah, it's still Kasner.
Yeah, but the strength of the coupling. So you have the exponential coupling e to the lambda phi. Mm-hmm. Would your results depend on lambda, or you didn't see any dependence on lambda?
Yeah, but yeah. So some this lambda right here, you mean?
Yes.
Yeah. So this plot would change, probably the numbers in this plot, but the sort of structure won't. I don't know. This might change. I'm not sure. Actually, that might be interesting. Actually, I'm not sure what would happen to this, but the qualitative story does not change, okay. As far as I know.
Thank you.
Yeah, we have a section on it in the paper. Yeah. Good. But actually, it's an interesting question more broadly, that because a lot of this dynamics is quite non-linear, I mean, adding a potential, I mean, changing the theory could make differences to various points, but not because phi ends up going logarithmically near the Kasner solution. That bit stays the same. I mean, the numbers change, but the qualitative picture is the same. Excellent. All right, so now let me talk about a charge one more step. So now we're going to do one more thing, which is now it's the same setup. So gravity, Maxwell, the scalar field, but now the scalar field is charged, which means that it couples. The scalar field is coupled to
So we have a problem with the connection, it seems. Is it here, or I don't know?
No, I can hear you.
Am I back?
Yeah, you are now.
Is it better? It was probably on my end. Most likely it was on my end.
Okay, so now we can see you again and hear you again.
Okay, thank you. Sorry. Okay, I don't know what the last thing you heard was. So did you hear?
So we heard that the scalar field was charged, but then you disappeared.
Okay, wonderful. Okay, good. So we have the technical coupling, and it turns out this coupling actually does some quite interesting things, which I will tell you about in the remainder. One thing that it does that was already known. So far I've been sourcing the scalar field, like explicitly turning it on at the boundary. It turns out that when it's charged, you don't have to. So if you take your Reiser-Nordstrom black hole in ADS and you cool it down, and you have a charged scalar field in the theory, below a critical temperature of the black hole, the charge will spontaneously condense. Am I still there? Mm-hmm. Yes. Yeah, very good. The charge will spontaneously condense, and you can think of this in the following way: that there's like a pair production. I mean, it's entirely classical. But if you imagine putting in a negative and a positive charge, the negative charge gets sucked into the black hole, and the positive charge wants to get pushed away from the black hole. If the charge is stronger than gravity, then that charge will get pushed away. But the boundary of ADS means that it can't escape to infinity, and so it sort of sits there. And so a bunch of charges go into the black hole, and they discharge the horizon. They neutralize the black hole, and you're left with the condensate that sits outside the black hole. Okay, so this is called holographic superconductors, and it's a form of hair on black holes in ADS. Okay, so the important point is I'm not going to put a source for the scalar field on the boundary. I'm just going to cool down, right, to Nordstrom, and below some temperature, a condensate will appear outside the horizon. Okay. Another way to think about this, it's basically this. Okay, so now I'm going to talk about what happens inside a holographic superconductor. Okay, so I have a black hole, and I have some condensate sitting outside, but of course, the solution will also change inside. Okay, so there are going to be two points. Firstly, I'm going to show you that when you have a non-zero charged scalar field, there are no Cauchy horizons. But now for any value, there's actually a much stronger theorem that there are no Cauchy horizons in this case. And again, there will be a Kästner universe and a collapse of the Einstein-Rosen bridge. But there's one more thing that happens. Okay, so let me tell you about this. So when you have a charge, there's an electric field outside the black hole. So what's an electric field? It's E, right? And E is the gradient of the electrostatic potential, which is like grad of A of T, right? So A of T is the electrostatic potential. But inside the horizon, remember T becomes space-like. And so inside the horizon, A of T is more like a vector potential. It's pointing, right? The A is now is pointing in a space direction. Now, I could ask you, what does a charged scalar field do in the presence of a vector potential? So the answer to that question actually won Josephson a Nobel Prize, okay? And which is that it oscillates. And so if I write down a charged wave equation, so I take the scalar field, forget gravity, okay, forget the gravity, just take this action here with some A of T, where T is now space direction. The wave equation looks something like this. And there's a minus sign here. Outside the black hole, there's not a minus sign there, but inside there's a minus sign. Okay, and it has to do with T being spatial now. So if I take a charged scalar field with a background vector potential, it oscillates. Okay, it wants to oscillate. And these are precisely Josephson oscillations, right? So if you look up the Wikipedia page on Josephson oscillations, you'll see this equation, right? Josephson is normally thought about as a phase difference, right? Josephson oscillations when you have a condensate with a phase difference, but you can do a gauge transformation that removes the phase difference, but it will introduce a vector potential. Okay, so it's the same thing. So what we expect is that this charge, the charged scalar field should start to oscillate inside the black hole in time, right? T is now time. Sorry. Z is now time, okay, and T is not time. So this tau, this is not T, right? This is the real time. And in fact, it turns out that what happens is that as you get close to a would-be Cauchy horizon, these oscillations become extremely strong, and they seed a kind of chaos that I think, maybe someone can correct me, but I think it's a new kind of chaos inside black holes. Okay, but so let's see. So we'll get there. So first, let me tell you about the Cauchy horizons. So here's the theorem that if you, so what I want to show that if you have a charged scalar field in a charged black hole, so these are both not zero, then you cannot have a Cauchy horizon. Okay. Right. Yeah, how does this go? Okay, so first one can show, okay, I'm not going to actually do the math, but I'm going to give you the logic of it. So firstly, you can show that on a horizon, if you have a charged scalar field, the AT has to vanish. Okay, of course, these are not quite gauge invariant statements I'm making, but I've fixed the gauge by taking the field to be real, the scalar field to be real, because it's a charged scalar field. So gauge transformations will change it by a phase. So this is implicitly in some gauge. But it doesn't matter too much. Okay, so AT has to vanish on the horizon, and the basic reason for this is that if you look here in this wave equation, you see there's an AT A squared, and what that really is it has a 1 over GTT in it, and GTT goes to 0 on a horizon. And so it turns out that to find a regular solution, the vector, this AT needs to vanish on the horizons. Okay. But secondly, you can show within this homogeneous setup that there's a certain quantity that has to be the same on all horizons. Okay, yeah, maybe this is too opaque. I'll go through it quickly and in case it's useful, but to elaborate would take a while. But it turns out this quantity, which is roughly the free energy, has to be constant on horizons. But if AT vanishes, that means this thing has to be the same on the 2 horizons. But this thing is the temperature, and the temperature is positive on the outer horizon, but negative on the inner horizon. And so it's not possible that it's the same. Okay. Yeah, that was probably too fast, but there is an argument there. If you're interested, you can look at it. Okay. So now so here's some typical numerics. So this is the bound. This is the horizon, and here's the far interior. Okay, so notice we're going over many orders of magnitude, and for this, it was good to have some collaborators that had a lot of experience with numerics, because you have to run the numerics over exponentially long periods, and there are terms in the equations which are exponentially small compared to other terms, and so it is subtle, even though it's just ODEs. And so okay, so there are 2 things I'm trying to show here. So this is the evolution of the fields inside the horizon, okay, with a charged black hole and a charged scalar field. And so one sees that there are some oscillations in the scalar field right inside the horizon, but they eventually settle down, and then you get some scaling behavior. And so this is the logarithm of GTT. So GTT has some power law behavior. Right, this axis is also logarithmic. So this is a Kasner. So okay, so you go inside the horizon, the scalar field starts oscillating like crazy for a little bit, but then it relaxes. You get a Kasner region, but then at very, very late times, there's this, what we call a Kasner inversion, where GTT was collapsing, and then it's GTT was growing, and then it starts collapsing again. Okay. And so let me talk a little bit about that. Okay, so the 2 new things relative to what I was talking about before is there are these oscillations, and there's this Kasner inversion, which starts to look, I assume you guys have been talking about this, it starts to look a bit like something bouncing off a wall. Okay, it has a little bit of that flavor. There's just one, at least in this one. Okay, so I'll talk about that in a second. So I want to talk a bit about what we actually did. So this is numerics. And we did something that, in terms of methodology, is a little different to what is normally done in the more formal community of GR, but it's very common in the rest of physics. And I think it's worth, it is rigorous, so I think it's worth emphasizing, which is a certain interplay between numerics and analytics. So, there's a bunch of coupled nonlinear ODEs, which you cannot solve analytically, but you do numerics. And then, and you get some interesting regime where, for example, there are these oscillations. Then you go to that regime, and there, using your numerical solution, we plot each term in the equation, okay? And then we just see, and it turns out that whenever there's something interesting happening, normally there's 2 or 3 terms that are large, and all the rest of the terms in the equation are small. So you drop those terms, then you solve the equation. Then, if you're lucky, the simpler equation you can solve analytically. You solve it analytically, you get a solution, and you see if it matches the solution. So you see 2 things. Firstly, you check that on your solution, the terms that you dropped are in fact small, right? Parametrically small. And so then it's self-consistent. And secondly, you check that it matches the numerics. And if that works, you get an analytic description that's it's self-consistent, but you wouldn't have been able to find it without the numerics, because there's like, 10 terms, and it's a nonlinear equation, and you don't know which terms to drop, right? So the numerics is crucial of course, maybe if you have some wonderful intuition, you might also be able to do it. But a mundane way to do it is to, the numerics is a guide. I guess the rest of physics has experiment as a guide, right? And you can you know the answer, and then you try to reverse engineer what the important terms are. Okay, so we did that, and actually it was quite good because we were able to get analytic descriptions of all the interesting bits, meaning the oscillations and these Käsner inversions and so on. I'm not going to go through them all, but we did. And in particular, what this allowed us to do, we got an analytic handle on the sort of whole solution as t goes to tc, and that's as the scalar field becomes very small outside the black hole. Okay, and remember from this collapse of the Einstein-Rosen bridge, that when the scalar field becomes small, that's when the response of the would-be Cauchy horizon becomes the strongest. And actually, when it becomes very strong, it's actually easier to understand. Okay, so let's come back to that in a second. So here's still a numerical plot. So this is now the Käsner exponent on the horizon as a function of the temperature of the black hole. So remember, there's this condensate outside, and we raise the temperature, and when you get to Tc, that's when the condensate goes to 0. Okay, and so that's the most boring outside. Tc is the most boring place, right? Because the condensate just becomes very small and it goes away. But it turns out that close to the singularity, this is an extremely interesting regime. And so as you can see, so as the condensate is becoming small, you have this very chaotic-like behavior. This is not in time, okay? This is a function of temperature, right? This is on the solutions. And actually, if you zoom in, it turns out that this exponent, okay, here I'm plotting P5, they're all related to each other. The exponent is given by cosine of 1 over t minus tc. And actually, we got that analytically by the process I just mentioned, and it also matches the numerics. So actually here we have numerics and superimposed with this plot. So there's an accumulation of oscillations. Basically what's happening is the following. So you have this Cauchy horizon. Sorry, that's not, so let me do that again. So you have your horizon, and then there's the Cauchy horizon, right? And so it turns out that when the solution comes, as the scalar field becomes very small outside, you get closer and closer to the Cauchy horizon, right? And the closer you get to the Cauchy horizon, the more extreme the oscillations become. And so the closer as phi becomes smaller, you get more and more oscillations in the scalar field before it kills the Cauchy horizon. And these oscillations leave an imprint in the solution. And that's why there's all these oscillations in the behavior of the singularity. This is like, again, this is the exponent of the singularity as a function of temperature, but it has to do with the fact that there are these violent oscillations as the scalar field turns off. Okay, so that's the first point. And then it turns out it's even better than this. Right, so let me go back a second. So that was all sort of happening here. Now, so the Cauchy, the would-be Cauchy horizon is somewhere here. Okay, it's not very far in. Right, as you get more and more oscillations here, this inversion also moves around, and it can become more or less sharp. If this inversion happens very quickly, meaning it's a very sharp inversion, meaning the bounce off this wall is very sharp, then it also triggers oscillations. And so, yeah, so you can get, sometimes you get more oscillations here. Actually, we don't have numerics for this, but because it's too hard, but I think it's what happens. And so it turns out that, right, at certain temperatures that actually accumulate near Tc, this late time Käsner inversion is very sudden and seeds a new round of Josephson oscillations. And this process can repeat itself recursively. And so for certain very specially tuned temperatures, you get an infinite discrete set of temperatures. Sorry, so for a discrete set of temperatures that accumulates at Tc, there's an infinite number of scaling epochs that are separated by violent oscillations. Right? So you know, just behind the horizon, you have some oscillations, and much later time, there's this Käsner inversion, which wants to just happen once in this theory. But if you have just the right number of oscillations at the beginning, the inversion becomes very sudden, and then you get a new bunch of oscillations here, And then for just the right number of these oscillations, you get another inversion later on. And so you get a series of Kasner epochs that are separated by these violent oscillations. And so it's extremely reminiscent of this cosmological billiards that Marc has worked on and that you probably heard about. But I think it's, okay, I'm not sure if it's the same in a different guise or whether it's something different, but it is quite interesting. It may be different because this charged scalar field seems to be playing a very important role. It's because it's the fact that you get all these oscillations that let you tune what is happening later. It's if you like, it's chaos by oscillations rather than chaos by exponential growth. Okay, all right. So to summarize here, so charged scalar fields can condense spontaneously about charged ADS black holes. The doorbell's ring, but I think it's not important. Now the inside, so the sorry, somebody's repeatedly ringing the doorbell. Can I have just 1 minute? I'll be right back. Now you know what?
Yes.
It can't be. You know what? It's fine. I'm almost done. Let me finish this page. You know what? It's fine. If it rings one more time, I'll go. So sorry about that. Okay. So the where am I? So the right. So charged scalar fields can condense spontaneously, and the inside of these holographic superconductors, it does not have a Cauchy horizon, so that we can prove. And close to TC, when the condensate is small outside, the interior has these very strong Josephson oscillations at the collapse of the Einstein-Rosen bridge. And these can lead to infinitely many Kasner epochs in the interior. And I think I'll skip this and just maybe quickly end with some open questions so that we have a bit of time for questions if there are any. So one thing is whether we can account for inhomogeneities. So everything that I've been doing has been homogeneous. And as I'm sure you know, there's this decoupling of spatial points that happens towards singularities that would be very interesting to incorporate in this setting, but we haven't. There seems to be some kind of interior chaos due to these charged oscillating scalar fields. And it would be really nice to know how that connects to the more usual mixed master BKL type things. You know, so these are sort of technical questions. And the more conceptual things is whether, you know, it's still a mystery in holography. So I haven't addressed the question of what does this interior actually mean from the boundary, right? All I've been telling you is if we do understand what this interior means from the boundary, the things I'm telling you about today are some of the things that we will see, right? Some of the structure that is there. But one possibility is that the holographic description of the interior should really happen at the singularity itself rather than at the boundary. And this Kasner's understanding what a generic singularity looks like is going to be crucial for understanding that. And I didn't really talk about this, but there's a lot of interest recently in evaporating black holes and these so-called entanglement islands that are inside the black hole. And so these things may be sensitive to the interior dynamics. And so one can ask how any of these things I've talked about relates to these so-called entanglement islands and black hole evaporation. And that's all. So thanks a lot.
Well, thank you very much.